Hello, my wonderful calculus students, and welcome back to Miss Bowman Rambles on YouTube slash videos for 45 minutes. Um, we are in just getting into Unit 4 right now, and so today we're going to go into the day 3 notes for Unit 4. Now, I will say, days 1 and 2, we started with just like right off the bat a real world application. We are like, here's related rates, here are these situations with moving pieces. Let's talk about their rates and how we would solve problems with that, aka the derivative. The next few lessons, what we're going to do is we're still talking about different applications of the derivatives, but we're going to switch gears a little bit and go back into the abstract and theoretical world. And so far this year, we've kind of only done one real theorem, which is the intermediate value theorem. We still have a few more, and so we're going to switch gears today and kind of talk about an abstract application of derivatives, and we're going to learn another theorem today known as the extreme value theorem. So we're going to go through what is the extreme value theorem and what does it tell us and what does it guarantee, since theorems are mathematical guarantees. And we're going to do that. We're also going to be investigating and kind of determining what we call the local or relative and global or absolute extreme values of a function. In plural, we usually refer to them as extrema, like the plural form of extremes. And so we're just going to start with a few definitions, okay? And so there are two really types of extrema that a graph has, what we call absolute, or what we can also call global, okay, and then local or relative. So let's talk about the difference between these two. How are they similar? How are they different? And kind of go into it. And we kind of did this in Math 4, so this should seem familiar to you. We're just going to kind of go about it again and then talk about like the calculus of this, okay? So absolute, or what we call global maxes and mins. If f is a function with a domain D, then we can say f of c is the absolute maximum value on D if and only if f of x is less than or equal to f of c for all x in D. So what is that meaning in English? That's saying that we would say that a function has an absolute maximum value or height on that domain if and only if all the other points of the function in that domain are less than or equal to that value. Okay. Notice that I'm not saying that point. I'm really saying that value because it can get a little tricky if we say point. And so I'm going to say the absolute maximum value as opposed to the absolute maximum point. Okay. Likewise, the absolute minimum value on the domain occurs if and only if all of the other heights of the function are greater than or equal to that value for all x's in that domain. Okay, so where this gets a little tricky is, so if I have a domain D and I have a graph that looks like this is the absolute maximum because it's the highest that graph goes. Now, if I had a function that looks like this, we would say that that is the absolute maximum value because that is all the other values of that function are less than or equal to the value at that point. Now, does that mean that we have an absolute maximum point? No, but we have this absolute maximum value of the function, that the function will always have to be less than or equal to that. It just happens to happen in an infinite number of places, okay? But we would say that this is the absolute maximum value of that function or the global maximum. Local, okay, is if we talk about an interior point in the domain, we have a local maximum value if and only if the function is less than or equal to that value for all x's in some interval containing C. So think like right around the neighborhood of C. If it is the highest value, then that is a local maximum. Same with local minimum. It's just kind of do. A local maximum can occur at an endpoint if the appropriate inequality holds for all x in some half open domain. So instead of saying C has to be like in between two, and we would call that a local max, I could say that this is a local max because if I look at just that part of the graph, okay, it is the highest value in that local thing. So all Absolute maxes and mins are also considered local maxes and mins. And the way I explain this is the following. You might have the largest neighborhood, the largest grocery store in your neighborhood might be a Mariano's, okay? Now that could also be the largest Mariano's in the entire world. It just happens to be the largest one in your neighborhood and happens to also be the largest one in the world. So all absolute maximums are considered local because they are in a neighborhood. Okay, but not all local maxes and mins are the absolute. Okay, so I want you to pause me and look at these three graphs. And I want you to identify all the absolute or global extrema of this function. So, what is the absolute highest? And then think if you were confused, was there what could we call local or relative? Okay, so pause me, think it over. What are the absolute maxes and mins for each of these? And then I will go over them. All right, welcome back. So if you look at this first picture, we have a closed domain. I would say the absolute maximum value that this function has is a value of 5. So I'm going to say there's an absolute max value of 5, and that occurs at x equals 2. So it is a singular case, and it is an endpoint, and that's okay because it's globally the largest value that function ever takes on. The absolute min of this function, the minimum value is 1, okay, at x equals 0. This is the absolute lowest value that that function takes on in its domain. Now, there is one other point I want to talk about, this point right here. In that neighborhood, if I draw a little box around it, it is the highest point in that neighborhood. So this would be a local max, okay, but it is not the absolute max. This is also a local max, and it's the absolute max of that function. This would be a local min and an absolute min. All right, let's look at this next one. Now, if I had to look at this next one, there's a little bit of difference here. So I'm just going to blow this up so we can talk about it. If I look here, these are open circles. So I can't say that there is an absolute maximum value because I can't define the closest thing. And I'm not going to say it's the limit because the limit is an intended value and we are looking for actual values. I will say, however, that we do have an absolute min of 1 at x equals 0. Okay, this graph, because of these open circles, we do not have an absolute max because these would be local maxes and neither of them are closed. And again, we cannot talk about an intended height. We could only talk about a actual height. And then here, the minimum value now, if I were to look at this point at x equals 0, the value of the function is actually 2, which is the highest value within that interval. So if I'm talking about this point, I'm actually, guys, going to say that this is a local max. And I know that kind of blows your mind, but if you think about the value of the function there, the value of the function there is 2, and all of the other points around it are lower or less than or equal to 2. So we would say that that is a local maximum, but there's no absolute minimum here because there's an open circle, and there's no absolute max because there are other places that are higher than 2. Okay, so knowing that in these three pictures, if I wanted to guarantee an absolute max or min, what would have to be true about the function to guarantee an absolute max or min? Now, if you said continuous, you are partly right. Okay. If a function is continuous, okay, then we are guaranteed to have, we think we should be guaranteed to have an absolute max or min, but this graph is continuous on its domain, and it did not have an absolute max and a min. It had an absolute min, but not an absolute max. So it has to be continuous on a closed domain. If we have a picture like the first picture that I gave you, if we are continuous on a closed domain, then we can guarantee that we have an absolute maximum and an absolute minimum in that interval. That, my loves, is the extreme value theorem. So the extreme value theorem is the guarantee that a function would have both an absolute maximum and an absolute minimum on that interval. So the hypothesis or the conditions is if a function is continuous on a closed. So that's the same hypothesis for the intermediate value theorem. Just an FYI, like IVT has the same conditions as EVT, which kind of makes it nice. If a function is continuous on a closed domain, then what I can guarantee, my conclusion, okay, the guarantee is that f of x has both an absolute max and min. Okay. Now let's talk a little bit about EVT, or extreme value theorem. I call it EVT for short. Feel free to do the same. All that extreme value theorem does is it tells me they have to exist. This theorem tells me nothing about where they exist, just that they have to exist. Okay, IVT guarantees that all the middle heights have to exist. Doesn't tell me where the middle heights are hit, it's just that they have to be there. So extreme value theorem is saying we have to have absolute maxes and mins if we have a continuous and closed interval. So what I want you to do is look at these next 4 graphs and kind of figure out where is the absolute max and min for each of these. Okay, I'm going to close some notes in your notes, like where is the absolute max and min on each of these? Okay, and circle that absolute max and min, and then we'll talk about whether or not they have anything in common. We're going to assume that all of these are closed and continuous functions. Okay, so you should have circled the absolute maxes and mins for this one. In this first picture, I have an absolute max of big M, an absolute min of little m, absolute max at A, absolute min at B. In the third picture, I have an absolute max at x2 and absolute min at A. In the fourth picture, I have an absolute max at B and an absolute min at x1. Okay, so if I look here and I'm thinking about what do all of these points have in common, okay, they all are one of 2 places. Absolute extrema can only occur at one of 2 places. Endpoints or critical points. Okay, so knowing if EVT applies will tell me that there's a max or a min. Okay, then if I know EVT applies, I can find them because I know they have to happen at one of 2 places, either the endpoints or what we call critical points. Now, critical points are as a vocab word I've been saying a couple of times throughout the year. We did it a little bit in Unit 2, but let's really define critical points for ourselves so that we know when I say the word critical point, what do I mean? So a point in the interior of the domain, notice it says the interior, we're not talking at the ends here, in the interior of the domain of a function f, at which the derivative is 0 or the derivative does not exist. Okay, that should say f prime, that's a typo. Okay. So we will have local mins and maxes at critical points, so 0 and undefined slopes, and they could also be global extrema. So how do we find global extrema on a closed interval? If I have a continuous function on a closed interval from A to B, then EVT applies, which means I have to have both an absolute max and min. I know that they're going to occur at one of 2 places, at critical points or at the endpoint. So what I'm going to do first is find all critical points. And then what I'm going to do next is compare the values of the function at the critical points, which I'm just going to call CP, okay, and endpoints. And the fastest way to do that is by making a table, and a table is awesome because it actually counts as justification. It'll give you the reason why. All right, so let's do a couple of examples of that. Here's example 3. f of x equals x squared minus 4x on the interval 0 to 5. So let's first determine if EVT applies. So are we guaranteed to have absolute maxes and mins? So if I am, I'm going to ask myself, okay, is f of x continuous? And the answer is yes. It's a quadratic function that's continuous. Is it closed? Yes. Okay, good. Then EVT applies. We're guaranteed to have an absolute max and an absolute min. We'll have both in this function. Now we know that those are going to happen at either endpoints or critical points. So now what I'm going to do is I'm going to find the critical points. Critical points are where the derivative is 0 or undefined. So what I would do here is I'm just going to find the derivative function, and then I'm going to set that function equal to 0. And on a free response, guys, this is worth 1 point, just knowing we have to find it where it's equal to 0. And when I do that, I get 1 critical point at x equals 2. Okay. Now, the second part, there is no place where this derivative is undefined, so I don't have to worry about the undefined slopes. But now I want to compare. So what I'm going to do is compare the function values, okay, at my endpoints and my critical points. And I'm going to check, is 2 within my interval? Yes, 2 is between 0 and 5. So I'm just going to make a table of 0, 2, and 5. And I put them in order because it just kind of helps me. So if I plug in 0 into the function, so we go back to the OG for our comparison. We're not comparing their slopes. We're actually comparing the function's values here. So if I plug in 0, I get out 0. If I plug in 2, let's see, 4 minus 8, I get negative 4. And if I plug in 5, I get 25 minus 20, which is 5. So if I look at those, okay, the largest value that I get in that table is my absolute max. So I have an absolute maximum of 5 at x equals 5, and an absolute minimum of negative 4, because that is the lowest number in my table at x equals 2. Okay. Now, if I asked you for locals, if we have an absolute max, that's also a local max. If we have an absolute min, that's also a local min. Then the other question is what's happening at 0, 0. And this is why I put this in numerical order, because I want to kind of figure out what's happening here. But I'm starting at 0 and going to a height of negative 4 and then going to a height of 5. I know this function is continuous, so it's not going to do anything weird in between. It's going to go straight from a height of 0 to a height of negative 4 to a height of 5. Okay, that means that what's happening at 0, if we compare these two, 0 is higher, 0 would be a local max. So I could add on that there's a local max of 0 at x equals 0. Okay, let's try another one. So we want to find the extreme values of this function. Okay. I'm going to check, is it continuous? Yes, I graphed it for us. Isn't that nice of me? But yes, if I look, there's no place that's going to be undefined, especially because x to the 2/3 is the same thing as the cube root of x squared. I can take the cube root of anything. Like there's nothing that's going to make this undefined on the domain. And it's closed. So is it closed? Yes. Is it continuous? Yes. So do we have to have absolute maxes and mins? Yes and yes. Okay, so first we have to find our critical points. So I'm going to find the derivative function. Now I'm going to have to use the power rule here. So 3 times 2/3 would be 6/3, which is just 2. 2/3 minus 1 is x to the 1/3. Okay. And so if I clean this up, I get 2 minus 2 over x to the 1/3. Now if I look at that, team, and I try to set this equal to 0, I'm going to get 2 equals 2 over x to the 1/3. That's going to give me 2 x to the 1/3 equals 2. X to the 1/3 equals 1. I would cube both sides to eliminate the 1/3 power, and I would get x equals 1. Is 1 within my domain? Okay, I found a critical point. The other thing I need to check is if my derivative function is undefined, because those are also critical points. So if I look at this derivative function, is there any x value that would make this function undefined? And the answer to that is yes, at x equals 0, because it's not in the domain if it's in the denominator. Okay, now is 0 within my interval? Yes, it also happens to be my endpoint, which is kind of nice. So now what I would do is once you find your critical points, we are going to compare the critical points to the endpoints. So we have 0 as an endpoint / critical point. 1 is a critical point, and 3 is an endpoint. And I'm just going to plug them back into the original function to figure out what is the highest value and what is the lowest value. So I get -1 when I plug in 1, and then if I plug in 3, I get 6 minus 3 times 3 to the 2/3. Okay, let's talk about how to estimate this. Okay, that's going to be the same thing as 6 minus 3 to the 5/3. Okay, that's going to be the cube root of 3 to the 5th. That's going to be like the same thing as 3 to the 5th and the cube rooted. That's going to be like, I don't know, 7-ish, 6 point something. Okay, that's some negative number. That's why I gave you the graph there so that you could compare it. You probably need a calculator here. But now I can say absolute min of -1 at x equals 1, absolute max of 0 at 0. Now, is the minimum always going to be the critical point? No. Okay. Is the maximum always going to be an endpoint? No. And that's how we would find absolute maxes and mins if EBT applies. Okay. Now, the question is, how do we find maxes and mins when EBT doesn't apply? If the function is not continuous or it's not closed, okay? Now, if we have a continuous function, then we can like sketch a graph. We can figure out like what are the limits and the horizontal asymptotes and figure out where if our function is increasing, decreasing, that kind of stuff. I know the possibilities for maxes and mins occur at endpoints or critical points. So what I would want to do here is I'm going to actually have to analyze some more behavior when I'm talking about finding the extreme values of a function. Okay, and if it's EBT doesn't apply and we don't have things like endpoints, then it's going to be a little bit trickier. And we're going to have to analyze just like what is happening in this function before we can decide, does it have absolute maxes and mins? Okay, so if I am given a situation that is not closed, the first thing I'm going to do is figure out the domain. Now here, in a function like this, I know I'm not allowed to divide by 0, and I'm not allowed to take the derivative, or I mean the square root of a negative. The derivative, I can take the derivative of a negative. So I know this radical actually has to be greater than 0. So what I would do is I would solve this little inequality, and I would think 9 has to be less than x squared. So the absolute value of x has to be less than or equal to 3. So here the domain is actually going to be between -3 and 3. Now, if you're like, Ms. Bowman, how did you just do that? Okay, I said x has to be less than 3, or -x has to be less than 3, which means x has to be greater than -3. Okay, and don't forget when you take the square root, that's why we have the absolute value. So I have my domain. The domain doesn't have any endpoints. So if it does have a max or a min, it can't be at the endpoints because there are no endpoints. This would have an open circle. So now what I'm going to do is decide, does this function have any critical points? So I'm going to rewrite this. And I'm going to bring that radical out of the denominator so that it makes it easy to use the power rule. And I'm going to take the derivative. So when I take the derivative here, I'm going to bring the -1/2 down. 9 minus x squared to the -3/2. Ooh, chain rule. Times the derivative of what's inside, which would be -2x. And I'm going to clean that derivative up. Okay, so the 2's would cancel, and I'd end up with a positive x over 9 minus x squared to the 3/2, and I'd move that to the bottom. Okay, so now I would need to figure out two cases. Where is the derivative equal to 0? And where is the derivative undefined? Well, it's equal to 0. If I set it equal to 0, I just get x equals 0. Is that in my domain? Yes. Okay, now I'm going to look at where it's undefined. Well, it's undefined when the bottom is equal to 0. So if I set the bottom equal to 0, I get x equals plus or minus 3, which is not in our domain, and we can reject that idea altogether. Okay. So what this tells me in this situation is that I have one critical point, okay? That's a possible max or min. Now it could be a leveling point. We're not sure which one it is. And so what I would want to do here is I would want to, I would want to just make sure that we can figure out what's happening. So what I would want to do is I'm going to test the slopes around x equals 0. If I know that the slopes are positive or negative, then that'll tell me what the function is doing. So I'm going to test the slopes here around this x equals 0. And when I do that, I'm going to make a sign test. Now we remember sign tests from Math 4, okay? I know that certain teachers do sign tests different ways. Okay, I'm going to do a number line sign test. So here's what I'm going to do. I'm going to say, okay, let me look at f prime and see what's happening here. Okay, now I know that my function only goes from -3 to 3. So I'm going to go ahead and put like parentheses at the ends at -3 and 3 because that's the domain of our function. And I'm testing the slopes around the domain. And then at 0, I'm going to label a point called 0, and I'm just going to put a 0 above because that's what f prime was equal to. Okay, I think Remus puts the 0 below, but it doesn't make a difference. All right, now what I'm going to do is I'm going to test what's the f prime values over here and what are the f prime values over here. So if I plug in something like -1 into this derivative, I'm going to end up with a positive and negative, which gives me a negative. If I test derivative values like 1, since that's over here, I end up with positive over a positive, which gives me a positive. Okay, now what does that tell us? And it tells us that the function has negative slopes before 0 and positive slopes after 0. Since we have negative slopes, we know the function is decreasing. And since the 0 to 3 is positive slopes, we know the function is increasing. So I would have an open circle, I would decrease, and then I would increase, and I would have an open circle. Okay, what that tells us is that f of x has an absolute minimum because it only has one change in direction and it has open circle endpoints. And it has an absolute minimum at x equals 0. Now to figure out what that is, let's figure out what that value is. Let's plug in 0 to the original function. That's going to give me 1/3. So it actually has an absolute minimum of 1/3 at x equals 0. Okay, so if EVT does not apply, your life becomes a lot harder because you have to do all this extra work to analyze the function because we don't have a guarantee. We have to like do some analysis to figure out, does it happen? Okay, so let's try two more tricky ones. All right, identify the critical points and determine the local extreme values for the function before. So does EVT apply? Well, I don't know. Let's see. Is this function even continuous? If I plug in 3, or if I plug in 0, I get 3. Okay, it is continuous. Is it closed? No, this is an open domain. Okay, if I were to sketch this function, let's think about how it would look. It would look something like that, and then, I don't know, something like this probably. Okay, something that to that effect. So here's what we're going to do. We're going to find the derivative. Since the domain is all real numbers, we already have that domain. What I want to do is I want to find the derivative and figure out if I have any critical points. So this derivative is -1. This derivative would be 2 minus 2x. Okay. -1 is never going to equal 0. There are no critical points on a linear function. So this function we do not have to worry about. Now, we will have to include this in our analysis, but the only turning point we would have would be for this function. So if I set 2 minus 2x equal to 0, I will get x equals 1, which is in the domain of that part. And so I know we have a critical point at x equals 1. So now what I'm going to do is I'm going to do an analysis. So I'm going to do an analysis of the slopes. This is called the first derivative test. Do an analysis of the slopes to see. Now I'm going to include 0 because the function has a corner at 0. Okay, I know that it has a corner because it has two different slopes. And I'm going to include 1 on here because 1 is my critical point. So I include the break in the domain, okay, where the derivative is undefined since there's a corner. And then here is where the derivative was 0. Now I'm going to test it into my slope functions to find out. Now anything less than 0 is always negative, so that's nice. If I plug in something like 0.5, 2 minus 2 times 0.5, well, half of 2 is 1, 2 minus 1 is positive. And then if I plug in 2, I end up with a negative. So let's think about what this function is doing. The function decreases, has a corner, increases, and then decreases again. So we decrease to a corner, increase, and then decrease again. So do we have any absolute maxes and mins? No, because this function is going to go down forever, and this function is going to go up forever, especially if I look at the horse. There's like no top heavy, bottom heavy Beyonce situation here. Okay, so this corner then has to be a local min because we go from decreasing to increasing. So there's a local min of, let's see, if we plug in 0, f of 0 is 3. So 3 at x equals 0, and a local max of, now I got to plug in 1 to my function, making sure I plug it into the right domain. That would give me 3 plus 2 minus 1. 5 minus 1 is 4, so local max of 4 at x equals 1. Okay, so let me go through this process again and just kind of summarize what we did here. Since this was a piecewise function, first I checked to see if it was continuous. I plugged in 3 into each equation. I plugged in, 0 into each equation, got 3 out, so I knew we had a continuous function. So what I had to do was look at where the derivative is 0 and where the derivative is undefined. So when I take the derivative of piecewise, if I compare 0 first to figure out if we have any place where the function is derivative function is undefined, these aren't undefined themselves, but at 0, I get -1 as one slope and 2 as the other slope. That's an undefined slope, so that's a critical point. So x equals 1 is a critical point, and x equals 0 is a critical point. Okay, then I set 2 minus 2x equal to 0, which I got 1, which was in that domain. Then I had to do a behavior analysis, aka a sign chart. And what I did was I looked at what kind of slopes did f of x have before 0, between 0 and 1, and after 1. And based off that, I know what the function's doing. And because we start from a positive infinity and end at a negative infinity, I know in this case there is no absolute maxes or mins, but there are local maxes and mins. A min anytime we go from negative to positive slopes, and a max anytime we go from positive to negative slopes. Okay, so we'll try one more. Find all global extrema of f of x without using a calculator. So for this one, what I want to do first is I want to figure out what my domain is. Now, if I set this bottom equal to 0 to find the domain, I get x squared equals -3, which can't be true. So the domain here is all real numbers. Okay, so I know that. Now the only then places that we can have possible maxes and mins are going to be at the end, or at the critical points. Since there's no endpoints, I have to test critical points. So I'm going to find my derivative. Ooh, low D high. Low d high minus high d low all over low, low. Now again, I never touch that bottom. It's completely simplified, but we're going to have to clean up this top. So I get x squared plus 3 minus 2x squared minus 2x over x squared plus 3 squared. If I clean that up a little bit more, I end up with negative x squared minus 2x plus 3 over x squared plus 3 squared. Now guys, I'm going to pull out a negative. This is my trick because I don't like negative x squared. So I just factor out a negative, and that makes that top totally factorable. And I will factor it. I get x plus 3 and x minus 1. And there's like an imaginary negative 1 in front. Okay, so there's my derivative. Now the critical points are going to be where the derivative is 0 and undefined. So I'm going to have to think, where is my derivative equal to 0 and where is my derivative undefined? Okay, this one does not apply. The bottom will never equal 0 in here. We figured that out in the domain, so we don't have to worry about that. Where is the derivative equal to 0? Well, because I factored that top, I can see if x is negative 3 or positive 1, then the derivative is going to be 0. So now I'm going to make a sign chart for my slopes. And I'm going to put negative 3 and 1, and I'm going to test it into this. Now what's nice is if I think about testing numbers here into the denominator, because I'm always squaring it, the bottom is always going to be a positive whenever I test. So all I really need to worry about then is what happens in the numerator. If I plug in negative 4, I have negative 1 times negative 1 times negative 5. That's going to be negative, and the function is decreasing. Now if I plug in something in between here like 0, I end up with negative 1 times positive 3 times negative. That's a positive. If I plug in 2, I get negative, positive, positive. That whole thing is going to be negative. Okay, so based off of that, I can see that the function decreases, then increases, then decreases. Okay, what I want to do is I want to figure out what is the point at negative 3, what is the point at 1, and also what height is the function approaching at the edges. So now that I kind of have an idea of what it looks like, I want to see what is the horizontal asymptote. So if I look at the limit as x approaches infinity here, I know it's reaching a height of 0 on both ends because it's bottom heavy. So now if I think about this graph then, if I plug in 1 to the original function, so if I find f of 1, which would be 1 plus 1 over 1 squared plus 3, I end up with 2 over 4, which is 1/2. Okay. If I plug in negative 3 plus 1 over 9 plus 3 gives me negative 2 over 12, which is negative 1/6. So I know I have a local max of 1/2 at x equals 1. I have a local min of negative 1/6 at x equals negative 3. Now, they're guaranteed to be locals because they are 0 slopes. Based off of this function, though, it's also the absolute, but I would only know that if I looked at, does this function go up forever or does it level out? So you have to consider not only what kind of slopes we have, but what kind of horizontal asymptotes would this graph have, and really analyze it to do it. And we'll kind of work our way towards doing most of these in this case. So if we had global extrema, yes, we do. We have a global max of 1/2 and a global min of negative 1/6. And that is absolute mins and maxes in a nutshell. Okay, let me know if you have any questions, and I will see you next time.